Hello, welcome back to another episode of Math with Haus. You're watching Precalculus Season 2, Episode 16. We're continuing our investigation of trigonometry, and in particular, we're continuing our investigation of transformations of sine and cosine graphs. So, in the previous two videos, we looked at the two following situations. Y equals some value times sine of x, and y equals sine of x plus some constant. So in the first situation here, we found out that this quantity a refers to what's called the amplitude, and if a is negative, it also became a rotation across the x-axis. Now, when we think about the second situation, y equals sine plus c, then what we had was a vertical shift up or down depending upon whether c was positive or negative. Now, our question is, what happens to our sine graph if we have something like 2 times x inside of it? So now what we're doing is multiplying the input variable by 2 inside the sine. So new situation, let's see what happens. So this is our example that we're going to have fun with. So we can start by making a table of values. So if x is equal to 0, well, then we get sine of 2 times 0, or just sine of 0, and sine of 0 is still 0. But now, when I plug in something like pi over 4, I get sine of 2 times pi over 4, which is equal to sine of pi over 2, which is equal to 1. If I plug in a pi over 2, similar story, right? 2 times pi over 2 inside our sine. This is the same thing as sine of pi, which is 0. And we can just plug in some more values, right? If I was to pick 3 pi over 4, we would find out this is a negative 1 because sine of 2 times 3 pi over 4, that's going to be sine of 3 pi over 2, which is negative 1. And if I plug in pi, then I get sine of 2 pi, which is 0. So to understand exactly what's going on here, we can recall our normal sine graph, right? So here's pi over 2, pi, 3 pi over 2, and 2 pi. And we need 1, negative 1. And our graph went up like this. Not the best looking graph, but you get the general idea. But now, what we have going on with our y equals sine of 2x, which I'm going to use the blue for. So we need our pi over 4 and 3 pi over 4. Alright, so now what we got is at pi over 4 we're at 1, then we go down to 0, 3 pi over 4 we're at negative 1, and then back up. So what happened is that what we're witnessing is called a horizontal compression. When we look at our graph, the normal sine curve, we can say has been compressed, right? In fact, it's been compressed by half. I could continue graphing this, and if we were to extend our table of values, we would see that this dotted line is how the curve continues. So what we see then is, since the graph is being compressed, if we recall before, we said that the period was 2 pi. That means in an interval of 2 pi amount, like from 0 to 2 pi or 2 pi to 4 pi, we get one full snapshot of our graph, because it just repeats this wave pattern for all of infinity. But now, with the blue curve here, we get our full pattern just in from 0 to pi. In other words, the period here is just pi. So that is a significant change. That means that when you take a value and multiply it by your independent variable inside a trig function, you are going to be affecting that function's period. Okay? So let's go ahead and define what we mean by period now. So a period, we could think of it as a value. In fact, a horizontal shift is a horizontal shift such that for your function f of x, if you were to plug in a p-value, let's see, in fact, we're going to insert p. So for a horizontal shift value, we're going to call p, f of x, f of the quantity x plus p would just give out f of x. So in other words, when you shift by a quantity of p to left or right, you just get the original graph again. So when we think about, say, 3 pi over 2 here on the blue curve, that's acting just like pi over 2 over here. That's because our p-value here is pi. So 3 pi over 2 minus a pi over 2 gives us this distance in between of pi. So that's what we're getting at here. The period is this horizontal shift such that if you have an x-coordinate plus a whatever this period is, then it's going to shift, or then you get out your original f of x, and that's what we have going on here. So when we just had y equals sine x, the period was equal to 2 pi. Now when we had sine of 2x, we saw that the period was equal to pi. So in general, if we have sine of, say, bx, to find the period, what you will want to do is take 2 pi and divide it by your b value. Right? So if we think about here, our quantity was 2, right? So if this was b equals 2, then you would have 2 pi divided by 2 giving you your pi. So if I had y equals sine of, say, 11x, then that means our period is going to equal 2 pi divided by 11. As simple as that. Now, there's one interesting feature about the change in period. For example, if y is equal to sine of negative 2x, well, this is really the same thing as negative sine of 2x. So if you have a negative inside, so if b is negative, then you also get that rotation across the x-axis, in addition to, of course, the period change. So when we are multiplying our independent variable inside of our sine, that will correspond to a period change. Okay. Now what we'll do is look at some graphs on Desmos so we can have some nicer pictures, because what we saw when we had sine of 2x was that we had a horizontal compression. So what happens if we pick something like multiplying our independent variable by a fraction? See what that does for us. So we have y equals sine x, y equals sine of 2x. I forgot my 2x. So we can see our horizontal compression here. Let's get our projector mode on. See that a little better, nice bold. Now here's y equals, say, sine of 1/2 times x. So a half times x. Notice how big our period got now. So we start at 0, and notice at 2 pi we're only halfway done. In fact, it goes out to 4 pi. So to explain what's going on there, we can just recall that if y is equal to the sine of 1/2 times x, that means the period is going to equal 2 pi divided by a half, which is the same thing as 2 times 2 pi, or 4 pi. Alright, so that explains graphically what we have going on here. And we can plot some other graphs just to get visuals. So let's change this to, say, 5. You can see how scrunched up that's getting, right? So our period would be 2 pi over 5, which we can see with the graph here. And we can, of course, extend this out much further, like we had a 10 here instead, right? Let's go ahead and hide that. So we can see how stretched out that became. Alright. There we go, there's our 20 pi right there. So you see how stretched out that became in comparison. That's one nice thing about this program Desmos, is you can see visually what's going on with a graph much quicker and easier than a lot of the graphing calculators. It's partly why I just love using this website. Alright, so to reiterate, when we have y equals sine of bx, then when b is greater than 1, we will have a horizontal compression. That means our period is going to get smaller, right? So our period is, our general formula for that is 2 pi over b. And when b is between 0 and 1, then we get a horizontal stretch. Because as we saw, the graph just gets stretched out. If you imagine a spring, and if you grab both ends and you just pull it apart, that's essentially what we're doing to our sine and cosine graphs, is just stretching it apart. Alright, if you've enjoyed this video, please subscribe to our channel, consider supporting us on Patreon. Thank you for watching this video and joining our math party, and I will see you next time.